In an MRI facility, addressing the conflicting requirements between NEC 517.13 and MRI manufacturer specifications, such as those from Siemens, requires careful consideration. NEC 517.13 mandates redundant grounding in patient exam rooms, including MRI rooms, typically involving a metal sheath and an insulated ground wire. However, MRI manufacturers often specify that branch wiring within the radio frequency shield should be on isolation transformers and be an ungrounded two-wire system. Here are some potential strategies to reconcile these differing requirements. One approach involves utilizing an isolated grounding system, or IGS. An IGS employs a distinct grounding electrode for each piece of equipment. This configuration minimizes ground currents flowing between different devices, mitigating interference and potential safety risks. IGS are frequently implemented in MRI facilities to segregate the MRI scanner from other equipment within the room. A second strategy includes implementing a bonding jumper. A bonding jumper acts as a conductor that establishes a connection between the metal sheath of the branch wiring and the insulated ground wire. This measure ensures that the metal sheath is grounded, while concurrently preventing ground currents from traversing the insulated ground wire. A third option is the implementation of a ground fault circuit interrupter, or GFCI. A GFCI is a protective device designed to detect ground faults and promptly interrupt the circuit. This functionality aids in safeguarding patients and staff from electrical shocks. GFCIs are commonly employed in MRI facilities to provide protection against ground faults occurring in the branch wiring. A fourth consideration involves direct consultation with the MRI manufacturer. The MRI manufacturer possesses the expertise to provide specific guidance on effectively meeting the requirements of both NEC 517.13 and their proprietary specifications. It is imperative to acknowledge that the aforementioned solutions represent a selection of possibilities. The optimal solution will vary contingent upon the specific circumstances of the MRI facility in question. Seeking counsel from a qualified electrician is paramount in determining the most suitable method for adhering to both the NEC and the MRI manufacturer's stipulations. Elaborating on isolated grounding systems, it's important to understand their design and implementation. An isolated grounding system typically involves running a separate insulated grounding conductor from the equipment back to the main grounding electrode system without connecting it to the building's normal grounding system at any point along the way. This prevents unwanted ground currents from circulating in the equipment grounding conductors, which can be a source of noise and interference in sensitive electronic equipment like MRI scanners. When installing an IGS, it's crucial to adhere to all applicable codes and standards, including those outlined in the NEC. The grounding electrode system itself must be properly installed and maintained to ensure effective grounding. The isolated ground conductors must be sized appropriately for the equipment they serve, and they must be protected from physical damage. Moving on to bonding jumpers, these are typically used to connect metallic parts of the electrical system together to ensure a low impedance path for fault currents. In the context of MRI wiring, a bonding jumper might be used to connect the metal conduit to a cable tray that contains the branch wiring to the equipment grounding conductor. This helps to ensure that any fault currents that might occur in the wiring will be safely conducted back to the source, stripping a circuit breaker or fuse and energizing the circuit. It's important to note that bonding jumpers must be properly sized and installed to be effective. The NEC provides specific requirements for the size and installation of bonding jumpers, and these requirements must be followed to ensure safety. Now let's discuss ground fault circuit interrupters, or GFCIs. GFCIs are designed to protect people from electric shock by detecting small ground faults and quickly interrupting the circuit. A ground fault occurs when current leaks from a circuit to ground. For example, if someone touches a live wire and provides a path for current to flow to ground through their body. GFCIs work by monitoring the current flowing in hot and neutral conductors of a circuit. If there is a difference of more than a few milliamperes between these currents, the GFCI trips, interrupting the circuit and preventing electric shock. GFCIs are commonly used in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. While GFCIs can provide valuable protection against electric shock, they are not a substitute for proper grounding. In fact, GFCIs rely on a properly grounded electrical system to function correctly. If the electrical system is not properly grounded, a GFCI may not be able to detect ground faults and may not trip when it should. Finally, consulting with the MRI manufacturer is crucial because they have specific knowledge of the equipment's electrical requirements and any potential safety concerns. They can provide guidance on how to properly wire the MRI scanner to meet both the NEC requirements and their own specifications. This may involve using special wiring methods, grounding techniques, or protective devices. The MRI manufacturer may also be able to provide training to electricians and other personnel on the proper installation and maintenance of the MRI scanner's electrical system. Ultimately, the goal is to ensure that the MRI scanner is wired safely and correctly, minimizing the risk of electrical shock, fire, or equipment damage. In addition to these specific solutions, there are some general best practices that should be followed when wiring an MRI facility. Firstly, all electrical work should be performed by qualified electricians who are familiar with the NEC and the specific requirements of MRI facilities. Secondly, all wiring should be installed in accordance with the NEC and any applicable local codes. Thirdly, all electrical equipment should be properly grounded to minimize the risk of electric shock. Fourthly, regular inspections and maintenance should be performed on the electrical system to identify and correct any potential problems. Remember that electrical safety is paramount, especially in a sensitive environment like an MRI facility. All electrical work must be done with the utmost care and attention to detail to ensure the safety of patients, staff, and equipment. In addition to the points already mentioned, consider the following aspects related to grounding and isolation in MRI facilities. Understanding the purpose of isolation transformers helps in MRI wiring. Isolation transformers play a crucial role in MRI facilities by providing electrical isolation between the power source and the equipment within the RF shielded room. This isolation is essential for preventing noise and interference from entering the MRI system, which can degrade image quality. Isolation transformers also help to protect patients and staff from electrical shock by isolating the MRI equipment from the main power grid. When selecting an isolation transformer for an MRI facility, it's important to choose one that is specifically designed for this purpose. These transformers typically have very low capacitance and leakage current to minimize noise and interference. They may also be equipped with special shielding to further reduce electromagnetic interference. Moreover, it is essential to understand the two-wire and grounded system within the RF shield. The two-wire and grounded system specified by MRI manufacturers for wiring within the RF shield is intended to minimize ground loops and circulating currents. Ground loops occur when there are multiple paths to ground, which can create unwanted currents that interfere with the MRI system. By using an ungrounded system, the only path to ground is through the isolation transformer, which helps to prevent ground loops. However, an ungrounded system also presents some safety challenges. In a grounded system, a fault to ground will typically cause a circuit breaker to trip, energizing the circuit. In an ungrounded system, a single fault to ground will not trip a breaker, but it will create a potentially hazardous condition. If a second fault to ground occurs on a different circuit, it can create a short circuit and cause a fire or electric shock. For this reason, it's important to implement additional safety measures when using an ungrounded system, such as ground fault detectors that can detect the first fault to ground and provide an alarm. Furthermore, you must know how redundant grounding works in NEC 517.13. NEC 517.13 requires redundant grounding in patient care areas to provide multiple paths for fault currents to return to the source. This helps to ensure that a fault will trip a circuit breaker quickly, minimizing the risk of electric shock. In an MRI facility, redundant grounding typically involves using both a metal conduit or cable tray and an insulated equipment grounding conductor. The metal conduit or cable tray provides a physical path for fault currents, while the insulated equipment grounding conductor provides an additional path in case the conduit or cable tray is damaged or disconnected. The NEC also requires that all metal enclosures and equipment in patients' care areas be bonded together to create a low-impedance ground path. This bonding helps to equalize the voltage potential between different pieces of equipment, reducing the risk of electric shock. Also understand that the IGS considerations in MRI suites are very critical. When using an isolated grounding system in an MRI suite, it's important to carefully consider the design and implementation of the system. The isolated ground conductors must be properly sized and installed to provide a low impedance path for fault currents. They must also be protected from physical damage and isolated from the building's normal grounding system. It's also important to ensure that all equipment connected to the isolated grounding system is properly labeled to avoid confusion. The labeling should clearly indicate that the equipment is connected to an isolated grounding system and that it should not be connected to the building's normal grounding system. The NEC provides specific requirements for the labeling of isolated grounding systems, and these requirements must be followed. Now, note the importance of coordination with the authority having jurisdiction. It's crucial to coordinate with the authority having jurisdiction, or OJ, throughout the design and installation process. The HA is the local electrical inspector or other official who is responsible for enforcing the NEC and other applicable codes. The AHJ can provide guidance on how to meet the code requirements and can help to resolve any conflicts between the NEC and the MRI manufacturer specifications. It's also important to obtain all necessary permits before starting any electrical work. The AHJ can review the plans and specifications for the project and can issue a permit if the work meets the code requirements. Regular inspections should be scheduled throughout the project to ensure that the work is being done in accordance with the approved plans and specifications. After the project is completed, a final inspection should be performed to ensure that all work has been done correctly and that the electrical system is safe and compliant. Keep in mind that proper documentation is paramount. Maintaining accurate and complete documentation of all electrical work is essential for future reference and troubleshooting. The documentation should include detailed drawings of the electrical system, including the location of all wiring, equipment, and grounding connections. It should also include a list of all materials used in the project, including the manufacturer, model number, and rating of each item. Test results should be documented, including the results of ground impedance tests, insulation resistance tests, and voltage drop tests. All documentation should be stored in a safe and accessible location. And you must focus on ongoing maintenance and testing. Regular maintenance and testing of the electrical system are essential for ensuring its continued safety and reliability. The electrical system should be visually inspected on a regular basis to identify any signs of damage or deterioration. Ground impedance tests should be performed periodically to verify that the grounding system is still effective. Insulation resistance tests should be performed to check for any insulation breakdown in the wiring. Voltage drop tests should be performed to ensure that the voltage at the equipment is within the acceptable range. Any problems that are identified during maintenance and testing should be corrected promptly. Remember that safety is always the top priority when working with electricity. By following these best practices and consulting with qualified professionals, it is possible to safely and effectively wire an MRI facility to meet both the NEC requirements and the MRI manufacturer's specifications. Think about the importance of surge protection. Surge protection devices, or SPDs, are designed to protect sensitive electronic equipment from voltage surges or spikes. These surges can be caused by lightning strikes, power grid switching, or other electrical disturbances. SPD work by diverting the surge current to ground, preventing it from reaching the equipment. In an MRI facility, SPD are particularly important because MRI scanners are very sensitive to voltage fluctuations. A voltage surge can damage the scanner's electronic components, leading to costly repairs or downtime. SPD should be installed at the main electrical panel and at any subpanels that serve the MRI equipment. They should also be installed on any individual circuits that power sensitive electronic devices. When selecting SPD for an MRI facility, it's important to choose devices that are specifically designed for this purpose. These devices typically have a high surge current capacity and a low clamping voltage. They may also be equipped with special filtering to further reduce noise and interference. Remember to consider harmonic mitigation as well. Harmonic currents are non-sinusoidal currents that can be generated by electronic devices such as computers, lighting ballasts, and variable frequency drives. These currents can cause a variety of problems in electrical systems, including overheating of transformers and conductors, increased voltage distortion, and interference with sensitive electronic equipment. In an MRI facility, harmonic currents can interfere with the MRI scanner, degrading image quality. Harmonic filters can be used to reduce the level of harmonic currents in the electrical system. These filters are typically installed at the main electrical panel or at any subpoles that serve equipment that generates harmonic currents. When selecting harmonic filters for an MRI facility, it's important to choose devices that are specifically designed for this purpose. These devices should be sized appropriately for the load and should be capable of reducing harmonic currents to acceptable levels. In addition to these specific considerations, it's also important to follow some general best practices when wiring an MRI facility. Use high-quality materials and components. All wiring, equipment, and components should be of high quality and should be suitable for the intended application. Use proper wiring methods. All wiring should be installed in accordance with the NEC and any applicable local codes. Use proper grounding techniques. All electrical equipment should be properly grounded to minimize the risk of electric shock. Use proper bonding techniques. All metal enclosures and equipment should be bonded together to create a low impedance ground path. Use proper labeling. All wiring, equipment, and components should be clearly labeled to avoid confusion. Keep the electrical system clean and organized. The electrical system should be kept clean and organized to facilitate maintenance and troubleshooting. Conduct regular inspections and maintenance. The electrical system should be inspected and maintained on a regular basis to identify and correct any potential problems. Work with qualified professionals. All electrical work should be performed by qualified electricians who are familiar with the NEC and the specific requirements of MRI facilities. By following these best practices, it is possible to safely and effectively wire an MRI facility to meet both the NEC requirements and the MRI manufacturer's specifications. Now consider leakage current testing. Leakage current testing is a procedure used to measure the amount of current that is leaking from electrical equipment to ground. This testing is important for identifying potential safety hazards such as insulation breakdown or faulty grounding connections. In an MRI facility, leakage current testing is particularly important because MRI scanners are very sensitive to electrical noise and interference. Excessive leakage current can interfere with the scanner, degrading image quality. Leakage current testing should be performed on a regular basis, typically at least once a year. The testing should be performed by a qualified electrician using specialized equipment. The results of the testing should be documented and any problems should be corrected promptly. In addition to leakage current testing, other types of electrical testing may also be necessary in an MRI facility. These tests may include ground impedance testing, insulation resistance testing, and voltage drop testing. The specific tests that are required will depend on the specific equipment and the specific requirements of the facility. It's important to consult with a qualified electrician to determine the appropriate testing schedule and procedures. Let's talk about magnetic field interference. MRI scanners generate strong magnetic fields that can interfere with other electronic equipment. For this reason, it's important to carefully consider the location of electrical equipment in an MRI facility. The electrical equipment should be located as far away from the MRI scanner as possible. If it is necessary to locate electrical equipment close to the scanner, it should be shielded to minimize magnetic field interference. Shielding can be accomplished by using metal enclosures or by wrapping the equipment with magnetic shielding materials. The specific shielding requirements will depend on the specific equipment and the specific magnetic field strength. It's important to consult with a qualified engineer to determine the appropriate shielding methods. As mentioned before, fiber optic cabling minimizes interference. Fiber optic cabling is a type of cabling that uses light to transmit data. Fiber optic cables are immune to electromagnetic interference, making them ideal for use in MRI facilities. Fiber optic cabling can be used to connect computers, monitors, and other electronic devices to the MRI scanner. This helps to minimize noise and interference, improving image quality. Fiber optic cabling is more expensive than traditional copper cabling, but it offers significant performance and safety advantages in MRI facilities. To reiterate, safety is paramount in MRI facilities. Electrical safety is a critical concern in MRI facilities due to the presence of high-voltage equipment, strong magnetic fields, and sensitive electronic devices. To ensure electrical safety, it's important to follow all applicable codes and standards, including the NEC. It's also important to implement a comprehensive electrical safety program that includes regular inspections, testing, and maintenance. All personnel who work in the MRI facility should be properly trained in electrical safety procedures. Training should include topics such as lockout-tagout procedures, arc flash safety, and proper use of personal protective equipment. By following these safety measures, it is possible to minimize the risk of electrical accidents in MRI facilities. It is also important to implement emergency procedures in case of an electrical accident. These procedures should include steps for shutting down the electrical system, providing first aid to injured personnel, and contacting emergency services. Emergency procedures should be posted in a conspicuous location and should be reviewed with all personnel on a regular basis. Now, let's consider the specific requirements for lighting in MRI facilities. Lighting in MRI facilities must be carefully designed to minimize glare and reflections. Glare and reflections can interfere with the MRI scanner, degrading image quality. Lighting should be indirect and diffuse to reduce glare. The color temperature of the lighting should also be carefully selected to provide a comfortable and relaxing environment for patients. The NEC provides specific requirements for lighting in healthcare facilities, including MRI facilities. These requirements address issues such as illumination levels, emergency lighting, and lighting control. In addition to general lighting, task lighting may also be required in certain areas of the MRI facility. Task lighting provides focused illumination for specific tasks, such as reading or performing medical procedures. Task lighting should be adjustable to allow users to customize the lighting to their individual needs. Finally, let's discuss the specific requirements for grounding electrode systems. The grounding electrode system provides a path for fault currents to return to the source, minimizing the risk of electric shock. The grounding electrode system should be designed and installed in accordance with the NEC. The NEC specifies the types of grounding electrodes that are permitted, as well as the minimum size and installation requirements. The grounding electrode system should be tested on a regular basis to verify that it is functioning properly. The test results should be documented and any problems should be corrected promptly. It's important to consider the specific requirements for supplementary grounding electrodes. Supplementary grounding electrodes may be required in certain situations, such as when the main grounding electrode system is not sufficient to provide adequate grounding. Supplementary grounding electrodes should be installed in accordance with the NEC. The NEC specifies the types of supplementary grounding electrodes that are permitted, as well as the minimum size and installation requirements. Finally, we can discuss grounding conductor sizing. Grounding conductors must be sized appropriately to carry the maximum fault current that is likely to occur. The NEC provides specific requirements for grounding conductor sizing based on the size of the overcurrent protection device. Grounding conductors should be installed in a neat and workmanlike manner. They should be protected from physical damage and should be securely connected to all equipment and enclosures. By following these guidelines, it is possible to safely and effectively wire an MRI facility to meet both the NEC requirements and the MRI manufacturer specifications. Remember that electrical safety is paramount, especially in a sensitive environment like an MRI facility. All electrical work must be done with the utmost care and attention to detail to ensure the safety of patients, staff, and equipment.